Welcome to the annual A.O. Williams Lecture. We consulted recently. This is, I think I am lucky to be the fourth chair to be introducing A.O. Williams lecturers. So it's a series which has gone, I think we're around 20 different lecturers, very distinguished people throughout the years, and you'll find out we have a very distinguished guest today. What I'm here to do is to tell you something about Arthur Williams, the namesake of this lecture series. And I have a history written by one of our former professors, Professor Robert Beyer, who was a bit of an armchair historian. He enjoyed writing things up, and he wrote this up about Arthur. Arthur Olney let's start again. Arthur Olney Street, Olneyville, right? Williams Jr. was a descendant of two prominent Rhode Island families, the Williams, who includes the colony's founder, Roger Williams, and the Olneys, Olneyville, whose forebears included Stephen Olney, Secretary of State in the cabinet of Grover Cleveland. Arthur grew up in East Providence, graduated from East Providence High School in 1930, entered a nationwide contest to find the brightest boy in America. It was a different era, okay? There were statewide examinations, and the winner in each state went to Menlo Park, New Jersey, where Thomas A. Edison lived. There was a final competition. The winner of that exam was to meet with Edison and to receive a 4-year scholarship, all expenses paid, to MIT. Arthur was the winner. Art graduated MIT in 1934, became Brown graduate student working for Bruce Lindsay, another big name in our department, on atomic wave function calculations, and then he moved on to the University of Maine, where he's a professor for 3 years. Luckily, he returned to Brown as a faculty member, where he was a faculty member for 30 years. In 1955, Professor Williams became chair, overseeing the expansion of the department beyond its strength in acoustics, starting solid-state and particle physics research in our department. In his own research, Art worked on underwater sound and was awarded the Pioneers of Underwater Acoustics Medal of the Acoustical Society of America in 1982. Now, in the words of one of our other professors who remembers Art very fondly, Professor Williams took a very generous interest in the younger faculty and helped give them a warm introduction to Brown. He was a gracious host at many parties at his house, and this contributed to the cohesiveness of the department. He was one of those faculty who contributed more to the university than grants and papers. With that, I turn it over to Ulrich Heinz, who will introduce our illustrious speaker today.
So after this introduction, yeah, it's my pleasure to introduce this year's Arthur Olney Williams speaker. So we welcome Professor Rolf Heuer to the department today. And Professor Heuer began his studies of physics at the University of Stuttgart in Germany, where he measured a cross-section of nuclei, of neutrons scattered off atomic nuclei. And while he thought nuclei are a little bit too big to study, he wanted to look at smaller things. And this was also the time that the JSI was being discovered, and so it was a time when things were happening in particle physics. So he ended up in particle physics doing his PhD, or his doctor in Heidelberg. And then from Heidelberg, he moved to CERN, where he worked on the Opal experiment. This is one of the 4 experiments that operated at the Large Electron-Positron Collider, which occupied the same ring that the LHC today occupies. And he realized that he didn't only want to look for small things, but he also wanted to bring people together and organize the team to look for small things. And so he eventually became the spokesperson of the Opal collaboration. Now that ended near around 2000, and he moved to Hamburg as a professor and became the research director for the German particle physics lab DAISY, which is in Hamburg. And finally, he has been the director general of CERN for the last 7 years. And again, there's lots happening in particle physics. This was the important period of bringing up the LHC and guiding it through initial bumps and successes, eventually to the discovery of the Higgs boson and beyond, we hope. So again, there's lots going on in particle physics. And so we're very pleased and honored today that the tables are turned. Instead of us being guests at CERN, Professor Heuer is a guest at Brown today.
Thank you very much for this introduction. Let me first say a few words to Arthur Olney Williams. I trained it to get it clearly spelled out. It was difficult to find something on the web about Williams, but I think you should put more on the web on it. Okay? And I will come back to that a little bit later for some other effects on him. Okay. So, breaking the wall of the hidden universe. I will talk about the discovery of the Higgs boson, about its implication on physics, mankind, and the early universe. But I will also tell you a little bit about CERN, because not everybody here knows what CERN is and what CERN does. And I will give at the end also a little bit an outlook, which is slightly more for the experts than for the others. But then you will have learned so much about particle physics that you will also appreciate the outlook for the experts. Okay. So one has to switch also these things on, and then it should work. What is the mission of CERN? The mission of CERN is fourfold. Well, first of all, of course, we want to push back the frontiers of knowledge. We want to unravel some of the secrets of the Big Bang. What was matter like at the early moments of the universe existence? One question is why? What is the reason that we physically can exist? Yeah? So this is one of the main, I think everybody should be interested in that. Yeah? Okay, so if you do that at the forefront of research, you have to be at the forefront of technology. So we develop new technologies for accelerators, for detectors, information technology. Here's my usual question, who is below 28? Well, that's good. You too? You forgot it, okay. I think you guys have never seen a world without the World Wide Web, okay? We were still working with punch cards. You cannot imagine what that means if you dropped your box of punch cards. It was rewriting the program, essentially. Okay. The web was born 1989 at CERN because our experiments were becoming so international, so large, that there needed to be a software package which allowed to distribute information quickly, reliably to all the places where people were allowed to have access. Okay? So that was the birth of the World Wide Web. Today, it's the grid computing, which is a driver in the cloud computing. And of course, we are also having quite some spin-off into society by medical applications, diagnosis, and therapy. Now, if you look at that, research, innovation, both at the forefront of today's knowledge, it's obvious that it's a fantastic training ground for scientists and engineers of today and of tomorrow. And here I have to correct immediately an image of CERN. We are not so much a physics laboratory. The physicists are coming in order to do their research. We are mainly an engineering laboratory. We need a lot of engineers in all kinds of areas in order to build, maintain, develop, etc., such an infrastructure. So I have much more staff in engineering and technologies than in physics. The physics is usually done by the researchers from the outside world. And that brings me to the fourth pillar, and that is to unite people from different countries and cultures. So we are not only breaking the wall of the hidden universe, we are also breaking the wall between cultures and nations. It's very important, especially today, to learn that one can work together in a peaceful manner. This is if you look around in the world, what happens at the moment, you need more such institutions which show that it's possible to work together. Okay, so CERN was founded in 1954 by 12 European states, and at that time it was science for peace. And you have to imagine, the whole discussion started 1949, shortly after the World War. A handful of visionary scientists, a handful of visionary diplomats were coming together, they resonated, and the resonance was called CERN. And it took just 5 years from the idea to the realization. So 1954, 12 European states, and that you can call science for peace. Today we have 21 member states, and we have made in 2010 a very, very important decision. CERN, the acronym stands for Conseil Européen pour la Recherche Nucléaire. So the E stands for Europe. Now, in 2010, we have made a very important decision. We have changed the meaning of the E from Europe to everywhere. And as a consequence, today we have 21 member states, because in the beginning of last year, Israel is the 21st member state, and Israel is outside all of the definitions of Europe. But if you look now, Israel is a member state. Now the applications for membership or associate membership, Turkey, Russia, Ukraine, Pakistan, Cyprus, it's still science for peace. Yeah? You see, these guys can work together if they want. And this is one of the main things which is fantastic at CERN, that you can show that people can work together. We have around 3,500 people on our payroll. As I told you, it's a lot of engineers and technicians. And we have between 11 and 12,000 scientists registered who come or are allowed to come to CERN to perform their experiment. So CERN is a European intergovernmental organization which is globally used. It is still 20 to 21, it's still mainly a European infrastructure. And the main thing is it's an infrastructure which belongs to all of its member states. It's an infrastructure which is so large that a single country cannot afford it. And therefore it is the infrastructure of that country also as a stakeholder. And it's a prime example of what Europe and its partners can achieve when they work together. 1954, it was European reconstruction. 1980, East meets West. I mean, it was vital to have an institute which could make the Iron Curtain in Europe transparent. So that was, again, very important in the understanding of East and West. Today, the LHC brings together more than 8,000 scientists. And the key message here is that from the very beginning of the existence of CERN, it showed it is a model of peaceful cooperation at the forefront of science, independent of cultural and national differences. Today, it has going beyond Europe, as I said, a global collaboration, and that is shown here. This is a distribution of all the CERN users by the location of the institute, not by the passport. We have roughly 100 nationalities registered, but by the location of the institute, and that's a spot check of January 2015. You see roughly 70%, or let's say 2/3 from the member states and 1/3 from the rest of the world. And people with good eyes can see that we are one of the largest US laboratories, because the US is the largest, has the largest amount of users, 1,700. The next one is, I think, Italy, if I'm not mistaken, with, I don't know, 1,400 something? Yeah, 1,400 something. So you profit a lot from the fact that research is free at CERN. Of course, you have to pay for your own experiment, but not for the usage of the infrastructure. But I think it's vital. It's really vital that research is free. It's open to everybody. Who passes the peer review, of course. Okay, and that shows you the age distribution of visiting scientists. It peaks at 26, while we have also some other people. Now I must say this distribution was done 5 years ago. So I know that everybody is now 5 years older. But why do I say that? Because 5 years ago, the LHC, or it's now 6 years I think, the LHC was not yet running. That means we did not have so many PhD students at the LHC. Today we have more than 2,500 PhD students performing their PhD with data from the LHC. That means the peak would be even higher at 26. Yeah? And so we are really, well, not the staff as you can see, but the users, they are really predominantly young people, and this gives also one of the vibrant aspects of CERN. So the question usually by funding agencies is, what do you do with so many PhD students? Where do they go once they have finished their PhD? And that's the answer. And the top graph shows, for those of you who have good eyes, that around 1/2 of the PhD, of the students, when they finish the PhD, they go directly into the private sector. The other half is still in academia, in universities or institutes. And in the private sector, around 1/3 of the private sector goes to computing, 20% here, for example, to engineering, the other 20% stay in physics. A small amount here, 4%, goes to finance. That was a few years ago. It was many more people going to finance. Well, you realize the effect of these people. So less and less people went now into finance. But that shows that, and this is very important, that we not only educate together with all the universities for academia, but also for the private sector. But of course, these people all come to do research at CERN. And CERN is not only the Large Hadron Collider, but CERN is also an institute with a lot of science at accelerators. Mainly you have the SPS, the superproton synchrotron, where the W and the Z boson were discovered and resulted in Nobel Prize. You have the PS and other smaller accelerators. That's better visible here. We have today around 50 kilometers of accelerator, starting with Linux, the PS, the booster, Isolde, which is an isotope factory, antiproton decelerator, SPS, and the LHC. And the science is done at all of these accelerators. So we have a rich program of accelerator-based particle physics, which you can see here on this slide. We have, of course, a high-energy frontier. We have hadronic matter, QCD, hadron structure, low-energy neutrino oscillations, antimatter research, heavy flavors, rare decays. Also, some small non-accelerator experiments on dark matter and astroparticle, climate research, and medical applications, a multidisciplinary approach. So around 1,000 physicists, 10% of our science visiting scientists are working on non-LHC particle physics. And the main message here is that this is scientific diversity at unique facilities. This is very important to show that these are things which can essentially only be done at CERN. And therefore, we maintain and upgrade all of these facilities. So we have a program for all of these facilities. But of course, the flagship, and this is all complemented and supported by theory. But now I concentrate on the high energy frontier on the LHC. Okay? So the scientific challenge is to understand the very first moments of our universe after the Big Bang. So when the universe expanded from a tremendously small, tremendously hot spot into today's size of 10 to the 28 centimeters in the course of roughly 14 billion years. Okay? I think it's extremely difficult to imagine 10 to the 28 centimeters. It's a huge number, but to imagine it is very difficult. It's equally difficult to imagine the very small numbers. What is the difference between, in the imagination, between 10 to the minus 12, 10 to the minus 13, 14? It goes to 0. I don't know if I can make that joke here in the US, but I try it. On the 10 to the 28 centimeters, I could help you a little bit, because if you replace the centimeters by dollars, you have roughly the square of the American deficit. It didn't help me very much to understand 10 to the 28. I can just say it's a large number, which, okay. So what we can imagine is, of course, the human dimension. That means the center of the ruler. And I put into the center of the ruler the only photo which I received from you on Williams. And this is my next complaint. Find a better photo for him, okay? It's not. It seems to be very difficult because I couldn't find anything. I did some research, but okay, fine. But I think it's worthwhile since you have this lecture series. I think would be. It was not a serious complaint, but I think it might be quite good. Okay, so now getting serious again. How can we now look into the history of the universe? Well, first of all, you can go to the large dimension. On the large dimension, you take telescopes. You take either ground-based telescopes, you take space-based telescopes. And it's obvious that the better the resolution, the more powerful the telescope, the further back you can look into history, into the history of the universe. Now, if you do that with photons, you run into a problem. I mean, you run up to the wall around 380,000 years after the Big Bang. In the first 380,000 years, the universe was still so hot that no stable matter could form, no stable atoms. So photons, that means energy and matter, was always fighting essentially against each other. So no stable matter could form, no photons, no information could escape, at least in form of photons. 380,000 years roughly after the Big Bang, the universe was cool enough so that stable atoms could form. The moment stable atoms could form, the photons could escape, and therefore the information you have is from the point of 380,000 years roughly after the Big Bang. Okay, so this is what I call the hidden universe. So what to do then? Well, you go to the small scale. And at the small scale, you need a super microscope. The more powerful your microscope, the smaller the scales you can resolve. The more powerful your microscope, the more energy you need in order to produce a small wavelength. The more powerful your microscope, the more energy you need. The more energy you have on a small spot, the higher the energy density. And with this higher energy density, you get close to the Big Bang. Now, how close do we get? But before I come to that, I want to stress again the difference. The difference is, here, with the LHC, we are reproducing the conditions at the moment of the early universe. With the telescopes, we are looking back. That's a big difference. With the telescopes, we are looking into the history. With a super microscope, we are reproducing the conditions. That's the big difference between the two approaches. And if you recalculate the resolution power of 10 to the minus 16, 10 to the minus 17 centimeters into time, then you find that we get up to 10 to the minus 12 seconds roughly to the Big Bang. So this is what I would call breaking the wall of the hidden universe, and I think nobody else gets closer than we get with this machine. Okay, I hope there are some people who are not from particle physics. Oh yeah, sure, yeah. I forgot. Okay. So what have we learned over that time? Well, of course, more than 100 years ago, Rutherford experiment showed that the atom can be divided into the nuclei and the electron. The nuclei in turn in protons, neutrons consisting out of the quarks and the force carriers, the gluons. And that is our standard model of particle physics, of the microcosm. You have here the matter particles, the quarks and the leptons, and on the right-hand side you have the force particles. So we have three families of 2 quarks and 2 leptons each. And I don't know if everybody of you appreciates very much that we all consist only out of 3 matter particles. The up quark, the down quark, 2 up and 1 down makes a proton, 2 down, 1 up makes a neutron, in turn makes a nuclei, the proton and the neutron, in turn makes the nuclei, and then you have the electron to neutralize it to the atom. These are the 3 matter particles out of which we are consisting. Now nature has 3 more families. Each counterpart of the up-down electron and the neutrino are heavier than in the lowest family. Still, we do not really know why we have 3 and only 3 families. Now, this is, of course, the metaparticle part. Now, these metaparticles have to understand how they should communicate, how they should interact, and for this we have the force particles. The photon is a carrier of the electromagnetic force. The gluons are the carriers of the strong force, which binds the quarks together, and also the nuclei, the nucleons in the nuclei. And the Z and W bosons are the carriers of the weak force, which is responsible, for example, for some of the processes in the sun. So these are the three main forces in the microcosm. We can neglect the gravitation because it's much too small in the microcosm. Fortunately, we can neglect it because we don't know how to calculate it together with the others. So this is a fantastic model. It just has 12 metaparticles and 4 types of force carriers. So very, very nice. But it has one problem. It was tested over decades with high precision. However, there was one crucial question left open, namely, how do elementary particles acquire mass? Now, some of you might think, why does this interest me? Well, it should interest you, because if the particles would all only be massless, we could just not exist. Because massless particles is essentially excluded to form composite matter. You need massive fundamental particles. And we need to understand how these guys got their mass. There's one possible solution, namely to define the mass as a property of particles with the energy E to move with a velocity normalized to the velocity of light. That is, and this is this formula, that means the higher the mass, the lower the velocity at the same energy. So mass equals 0, you have the velocity of light. We discussed this morning with some of the undergraduates that there was once the idea of, or the measurement unexplained, that there might be some particles faster than light. It was some time ago. That was wrong. So velocity of light is really the limit. And the higher the mass now at the same energy, the lower the velocity. So what can you do? You introduce a scalar field. And these were the 6 theorists who introduced that scalar, such as idea of a scalar field: Prout, Angler, and Higgs, and then Kippel, Goralnik, and Hagen. And Goralnik was working here at Brown. And the particles acquire the mass through the interaction with this field. Okay? The more they interact with this field, the heavier the particle. The less they interact with the field, the lower the mass of the particle. That's the trick. We would not know anything about this field if that field would not have a self-interaction. So the self-interaction of the field is then the so-called Higgs particle. It's a fluctuation in the field which from time to time appears and disappears again. The lifetime of the Higgs, I think, is 10 to the minus 20 or something like this, seconds. So particles acquire mass through the interaction with this field, and the self-interaction of the field is a Higgs particle. So the question is now, has the LHC answered the crucial question which was left open, namely how do elementary particles acquire mass? Or in other words, do we have the last missing cornerstone of the standard model? Did we find it? Well, there was an announcement, as you well know, on the 4th of July 2012, and I will come back to that. But there are many more key questions in particle physics open. The standard model, the first one is the origin of mass, which we have hopefully solved now. But the standard model leaves many other questions open. Is there a possible unification of forces at the highest energy? That means at the gut scale, close to the Big Bang energy. Is there a fundamental symmetry of forces and matter? Because force particles and matter particles have different spin symmetry. And we have to see, can we combine that to a fundamental symmetry of both? What happened to antimatter? After all, we are living in a matter-dominated universe. Where is the antimatter? And why is a little bit of matter left over from after the Big Bang? In how many number of space or time dimensions are we living? And then finally, the tiny question, what is dark matter? What is dark energy? After all, the standard model just describes roughly 5% of the universe, the visible universe. 95% of the universe is dark. The dark matter, 1/4 roughly is dark matter, 3/4 is dark energy. Dark matter clumps like normal matter, and dark energy drives the universe apart in an accelerated fashion. And it drives it apart in all directions in the same way. That means there's no preferred directional evidence in the dark energy. That means it's a scalar. That means it behaves all the same in all directions. That's important. Okay, the hope now is that with a Large Hadron Collider, we are entering the dark universe. And I have put an exclamation mark and a question mark in order to be on the safe side. The first one expresses the hope, and the second one the doubt, because you don't know. But this is something which drives us on, of course. Okay, so that brings me to the Large Hadron Collider, the LHC, 27 kilometer circumference, one of the largest scientific instruments ever built. Many more than 10,000 people were involved and still are involved in design, construction, exploitation now. It collides protons to reproduce the moments of the early universe 40 million times a second. That shows you some of the hardware of the Large Hadron Collider. This is one of the magnets. It's around 15 meters. I always forget the dimensions. I think it's around 15 meters long, and we have roughly 1,400 of these. We have only one position where we can lower it down. And then it is transported to the position where it will be installed. You see, I have the impression this guy looks pretty tired, which means it's one of the last magnets which was installed. Well, actually, this guy is only there for safety because this white line guides the whole track. So it's an automatic car. And then once you have it installed, you have to connect the magnets. And these are high power connections. There are more than 10,000 ampere flowing through these connections. And this was one of the 10,000 connections which blew up in 2008. And where we had to repair then in 2009 and to improve everything in order to make the machine now fit for higher energy and for a long lifetime. And this is, of course, the way I, as a DG, want to see the LHC. Nobody is in there. Everything is installed. We can start working. Now, to study, how do we do it? Well, in these blue magnets, we have two vacuum tubes. In each vacuum, in one vacuum tube, the protons are running clockwise, in the other one anti-clockwise. And at 4 positions where we have the big experiments, we bring these protons to collision. We don't have single protons. We have around 2,800 packets of protons. Now, for those who work in CMS, I know that in the past 3 years we had 1,400 packets. But it's designed for 2,800, and we will soon have 2,800 this year. So 2,800 packets running clockwise and anti-clockwise. More than 100 billion protons per packet, per bunch. Now colliding these bunches, if we don't do anything, results in nothing. The protons will not hit each other. So what you have to do is you have to squeeze, you have to focus these bunches before you want to collide them, then you collide them. And once you squeeze it well enough, then several tens of the protons will collide and therefore break in these collisions into their fundamental constituents like the quarks or the gluons. And these constituents then interact at a very high energy density, much higher than much higher than the energy density and the energy in the sun. But as I said, in a very small confined space, namely on the size of the proton. And this is a very high energy density. And out of this high energy density, a lot of particles come out. You transform this energy into particles. And the production and the decay of these new particles, which are coming out there, are registered in these high-tech, powerful detectors, which act like digital cameras, which are built around these interaction points. And I have a short movie which indicates that, to the ones who have not seen a collision yet. That is the LHC, at least the magnets. So then you see here soon a proton, and in the proton you see the three quarks, up and down quark, and then you collide the protons which come from the right-hand side and the protons which come from the left-hand side in these high-tech powerful instruments. And then a lot of particles come out. And you register these particles, you interpret these images, and out of the interpretation of these images, you can draw conclusions on the process, underlying process at the collision. What you see here is these detectors are built like onions, and each layer of the onion has a different task, a different job to perform. For example, the inner layers are registering the white tracks. The white tracks are charged particles. They all essentially stop at a certain moment. They lose their energy. They are getting absorbed, except for the muons. And you see here there are 2 muons going to the left and 2 muons going to the right. And you should remember these 4 blue tracks now for later. And you see that you can identify them as muons because, first of all, they are charged tracks, and secondly, they traverse the whole detector. So when we started with the LHC, we started a new era in fundamental science. And you see the 4 big experiments which are built up here, and 3 which are shown here, and 3 small experiments. Atlas is the biggest experiment. The second biggest is CMS. The C stands for compact. These are the 2 omnipurpose experiments. That means they should register all interesting processes in these collisions. LHCb is an experiment which in particular looks for heavy quark physics, which could give some indication on the difference in properties of matter and antimatter. And the ALICE experiment is dedicated for the heavy ion collisions when we, from time to time, collide lead ions with lead ions. To give you an idea about the size of these experiments, this is Atlas at the moment of construction. Now it's filled with around 100 to 150 million sensors. And you see this is the size of an average physicist. You can well imagine that is around 25 meters times 25 meters times 45 meters in longitudinal direction. You need to have such large detectors in order to resolve the smallest possible dimensions. Now, Brown is very strongly involved in CMS. And CMS, which is slightly smaller, again, you can see it here with in relation to the humans. CMS, as well as Atlas, has around 3,000 members from roughly 40 countries. Now, you have to imagine 3,000 members means, I don't know, one full professor has roughly 10 people in his or her group, which means, let's say, 300 professors, which means 300 egos. Yeah, he agrees, yes. Yes, I think it's a job of, egos. But it works. It really works. I mean, everybody knows that alone you cannot do it. You need the others. Yeah? So this is a fantastic sociological experiment also. So large international collaborations are a place where people learn to work together. It is collaboration and competition. One should not think that it's only collaboration. It is also competition. And I must say, science without competition doesn't work. You need competition. But you can compete and collaborate at the same time. You learn that diversity is a good opportunity to recognize differences, to accept them, and to learn to use them. It influences your way of thinking. You have to share information. You have to give and you have to take. I mean, if you don't give, you cannot receive anything. You have to work together. And I must say, how is the management? The management is really through common goals or by convincing partners. That's the only management which works here. But it works very well. And if it works very well, then, of course, we can address some of the key questions of particle physics. Will we understand, for example, this primordial state of matter before nucleons could form? That means roughly a microsecond after the Big Bang. Have we now finally found the Higgs particle? will we find the reason why antimatter and matter have not completely destroyed each other? And the tiny question, what is the mysterious dark matter and what is dark energy? These are questions which we can address, and if you look closely, I did not say which we can solve, but we will be able to address. Now, the problem now is, this is the cross-section, the production rate of various processes at the LHC. That's the total cross-section, everything together. Most of it here is standard model, which we know already. And below, down here, at the low energy, this is the energy of the collider, for example, this is 70 eV. The new physics is very much lower than all of the processes. You see, there's more than 10 orders of magnitude difference between the total reaction rate and the rate of new physics, which means you need a tremendous amount of statistics in order to produce new physics. But if you produce new physics, that doesn't help you. You have to identify the new physics. That means you need even more statistics, or in total you need a very high statistics, you need a high collision rate, and you need many years of data collection. That's a key message. Now, if you produce such a lot of collisions, such a lot of statistics, you need a fifth experiment. And the fifth big experiment at LHC is the worldwide LHC computing grid, which connects nearly 160 sites in 35 countries in a sort of grid-like computing, where you have a tier 0 at CERN and in Hungary. We have, for business continuity, we have two tier 0s. Then we are connected to 13 tier 1s. It's more than on the slide here. And then we have the tier 2, which is simulation and end-user analysis. It's an international collaboration to distribute and analyze the LHC data. And without the grid computing, without the fantastic work of the experimenters, and without the great performance of the machine, we could not have made the discovery in 2012. Now, let's concentrate now on the question, have we found the Higgs particle? This is again the graph. The production rate of the Higgs boson is rather low compared to the total production rate. But now comes the problem that you have to identify the Higgs boson. And this beast, of course, is special because it reacts, it interacts with all fundamental particles. That means it can decay in different ways in all fundamental particles. That means you have a lot of different decay possibilities of the Higgs, a lot of different signatures in the detector. So you have a low production rate and you have a low rate in each of these channels. And then you have to select for the detection the most promising, the cleanest channels. And one of the clean channels is the decay into two sets, and the two sets in turn decay, for example, into two muons. So you have two. You remember the two blue tracks to the left and the two blue tracks to the right? These were the four leptons, the four muons coming from a ZZ decay. Another very clean signature is the decay of the Higgs into two photons. And that could look like this. In the CMS experiment, for example, you have quite a few of charged tracks here, but then you have an accumulation of energy here. And this dashed line is only to guide the eyes. So there's no charged particle track. So this is a photon here with very high energy, another photon with very high energy. And both together, you form the invariant mass of these two photons. Now, despite the fact that it's a clean signature, there is background from standard model processes. Now, if you have background from standard model processes, your distribution of the invariant mass must be not a straight line, a continuous line. If you have a bump on this continuous line, a resonance, then you have found something new. And that was the discovery in July, the announcement in July 4, 2012. You see, that's the background from standard model as a function of the invariant mass of the two photons. And then on top of this, you have here the bump, which is the possible signal of the Higgs boson. And both experiments have shown that that they had signals in the two photon channel, in the four lepton channel. And that is now a very educational slide about the evolution of that signal. And for those of you who realize that I might express it wrongly, I usually get it wrong when I explain this graph. Okay. So this was the status on July 2011 at the European Physical Society meeting. What is shown here is the probability that it is not a signal. I think I got it right this time. It's a probability that it's not a signal. No, it is the probability that it's not a fluctuation. Jetzt bin ich wieder irritiert. Okay. If there is a fluctuation, then you should see a lot of these signals, but at a low amount of probability. The lower the probability here, the stronger the signal, the stronger the indication that there is a signal. Now I got it right. Okay, so if you have indefinite statistics, everything should be at 1, and there should be no fluctuation if there is no signal. If there is a signal somewhere, you should see it as a negative resonance here. That is now the signal as we had it a few months later in December 2011. And you see now all these fluctuations are gone. It's essentially everything is flat around 1, except for this 1 sigma. But then here we had already a 3.5 sigma, or a probability of 10 to the minus 4 nearly, that it is not a fluctuation. That it is a fluctuation. Now, it is difficult to do that each time, especially once it is now 11 o'clock in the evening. Okay. So then, in spring 2012, the first publication appeared, and then the signal went a little bit back. But again, this is really also a message to the young people. If everything always goes in the same direction, something must be wrong. There must be some fluctuations also in the evidence. So that didn't concern us. And then came the July 2012, and you see we had a 5 sigma effect that there is something new. And everything else, at all other places, it is flat at 1. So it's clear that's a clear evolution over 1 year from, let's say, a 2.5 sigma effect to a 5 sigma effect at one place. And when it was published finally with an analysis of more data, it went to nearly 6 sigma, and today we are much beyond the 6 sigma in each of the experiments. But I think this is a textbook example of how things are going within a short time. 1 year is a short time in particle physics, but it shows the way how such signals evolve and that it takes time to really announce a discovery. And I can tell you here, at the time of the EPS, when we had 2.5 sigma, we had a press conference. And one of the journalists was asking me, what is going on? Why can't you announce already now a discovery? So I looked at him and told him, look, we need more statistics, we have to be more sure, so we need patience. And then he answered, but we journalists are not patient. Then I looked at him and I smiled at him and I said to him, but maybe you can learn it. Afterwards, he made a very nice article out of this. And then in December, when we were at 3.5 sigma, a journalist came to me and said, do you remember me? I remembered him. I just got the newspaper wrong, but it doesn't matter. And he said, I'm the journalist whom you asked to be patient. And he said, look, I have learned it. Isn't that great? Yeah? You can educate journalists through that. I'm not sure if I made a mistake now, because I think there's an AP journalist in here today. You are there? You ignore that. Okay. No. Okay. No. It's very nice. It was a very nice discussion with him. Okay. So, the question is now, is this new particle really a Higgs boson? And for that, you have to verify the 2 most important fingerprints. One fingerprint is, does it couple to the fundamental particles according to the mass of the fundamental particle? That means, and that is shown here. That's the coupling strength of the Higgs of this particle to other particles as a function of the mass of these particles. You have here the top quark, W and Z boson, and the light particles like the tau lepton and the bottom quark. And it's a clear line dependence between the coupling and the mass of these particles as predicted here by the standard model. Of course, still with a large error bars, and I know I don't have the most up-to-date plot here, but it shows clearly the coupling is as predicted by the standard model. Secondly, the experiments have measured the spin of the particle. It's 0. It represents a scalar field, which is very important for this theory. So both fingerprints have been verified. So the answer is yes. It is a Higgs boson. It completes the standard model in that way, describing around 5% of the universe. Well, yes, it took us 50 years for 5%. But I still say it is a Higgs boson. I'm not talking about the Higgs boson. So the Nobel Prize in Physics was given in 2013 to François Englert and Peter Higgs. Robert Braut, the co-author with François Englert, had unfortunately passed away a few years earlier, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of the subatomic particles, and then confirmed through the discovery of the particle by Atlas and CMS at CERN's Large Hadron Collider. That is a fantastic one-sentence acknowledgement to the theory and experimental efforts. Now you have to remember they both wrote independently, completely independently from each other, their theory 1964. So it took 48 years to find the beast, to find that particle. And it took also 48 years, because they have never met before. They met the first time in 2012 at the announcement of the discovery. But the discovery of this Higgs boson is only the beginning, so what's next? The question is it the Higgs boson or one of many? The Higgs boson would mean it is the one of the standard model and nothing else. But the standard model now predicts all the properties of this Higgs boson. If one of the properties deviates from the prediction of the standard model, then you find new physics. And when you find new physics, if you measure with precision the properties, then the properties could give information on dark matter, because dark matter particles would influence these properties. And if you are very lucky, the properties could give first indications on dark energy. And I remind you that 95% of the universe are consisting out of dark matter and dark energy. So at least my understanding of the universe is going to change. And I think if we are lucky, we are really at the threshold to open the door into the dark universe. This is why we now have a physics program at the Large Hadron Collider far beyond 2030 for the next 20 years. And soon the LHC will run at a higher energy, opening a new window, hopefully, into this dark universe. We will produce many more Higgs bosons to investigate the properties. And if you look at the post-H126 discovery, what is going on? We really just begun the search beyond the standard model. Much has still to be accessed. There will be new physics models produced. There will be precision and rare physics beyond the direct production reach. The LHC is not only a superb energy frontier machine, it's also a superb intensity frontier machine. With all this intensity, you can measure very, very precisely, and I would never have dreamt 5-10 years ago that the LHC could be such a precision machine. It's fantastic what you can do. That's a message to the funding agencies. It's clear that investment is critical. We have this fantastic machine. We have to keep it going with powerful detectors, triggers, computing. And we should always remember that the LHC is the only Higgs top ZW factory on the planet for many years to come. We just have to exploit that. And one of the candidates for dark matter could be, beyond the Higgs indirect measurements, could be supersymmetry, which demands for each standard model particles a supersymmetric partner. And this supersymmetric, the lowest supersymmetric partner, could be a candidate particle for dark matter, and that would be the only machine where we could produce dark matter in the lab and then investigate it. And that's an example how supersymmetric particles could be produced at the LHC. You would have heard it if you would have found something. So no supersymmetric particle discovered yet. However, the potential for discovery of SUSY is sizable in the coming years. First through the energy increase which we have, and secondly then later through the intensity. So there are many years to go, and it's not, nobody should dream that we would, if SUSY is there, that we find it like this in the very first days. It might take many years. And this is why the European strategy for particle physics has identified 4 activities that have to be carried out with the highest priority. And Europe's top priority should be the exploitation of the full potential of the LHC, including the high luminosity upgrade of the machine and detectors. So that was the European strategy in 2013. Now last year, the P5 report has been published. P5 is a particle physics projects prioritization panel. Huh? But P5 is much easier. The LHC upgrades constitute our highest priority near-time large project. So there's a correspondence between the two strategies. Therefore, the key message here is there's a program at the energy frontier with LHC beyond 2013. 7 and 8 TeV have been done. 14 TeV design luminosity is coming. And then 14 TeV high luminosity, the high lumi LHC is coming in roughly 10 years from now. So, but upgrades to the accelerator complex, detectors, and computing grid are vital to fully exploit the physics potential of the LHC. And that is shown by these 2 statements from P5 and on the European strategy. And that's the high lumi LHC project. There's a major intervention needed on more than 1.2 kilometers of the LHC. New high field magnets, triplets, in the inner triplet, the focusing magnets, short dipoles, etc., have to be done. And this is all carried out in an international collaboration. And you see here the new elements of dipoles and of quadrupoles and dipoles. And you see there's 3 times the American flag. So there's a lot of international collaboration between the US, CERN, and some individual countries in Europe, and also Japan here. So national laboratories, but also industrial firms are involved in that. So that is number 1. Then out of the 4 activities, the next one, then the next 3 are on equal footing, but we, CERN, should undertake design studies for accelerator projects in a global context with an emphasis on the high energy frontier, proton-proton, electron-positron. And that shows you why we have to do it. That was a time where I was still working as a researcher. That was during lab time, and you see the construction started 1980. But at the time of the construction of lab, the first ideas on LHC, on design and R&D, started around 1984. So lab was running with physics and its upgrades until the beginning of 2000. Then the construction of LHC started, and the physics started in 2010. Today we are here. Well, I have to move that, we are here. Doesn't change the picture. And the high lumi LHC, the design started already at the construction phase of the LHC. So if you look at that, the time frame is that you need at least 30 years, 40 years for such a project. That means it's now high time to start to discuss the next study. Not yet the project, but to discuss the next study. No, it's true. And this is the future circular collider study, which is geared towards proton-proton collision towards 100 TeV. We had a kickoff meeting last February last year in Geneva, and the first collaboration meeting in March 2015 here in the US in Washington. And you have to do it now if you want to have a project in 10, 15, 20 years. So what is the idea? We want to have a conceptual design report ready and a cost review for the next European strategy update in 2018-19. It's an international collaboration. We have now signed more than 50 MOUs with institutions all over the world to study as a driver proton-proton collisions, as a potential intermediate step E plus E minus, and then as a potential option proton-electron. If you have such an infrastructure in the Geneva area, this is the LHC, and this would be a future circular collider. It traverses the lake. The lake is relatively shallow. If you are lucky and you get the water out, you have free cooling, but okay. we try to avoid that. But if you have such a large infrastructure, a new one, you have to study all possibilities which you can do with this infrastructure. But the driver is the hadron-hadron collision. At the same time, of course, we are continuing our linear collider studies. So this is a compact linear collider near CERN, which could reach eventually 3 TeV of electron-positron collisions. And there the conceptual design report is already published, but R&D continues still at CERN and in a collaboration, worldwide collaboration inside the CLIC effort. But CLIC effort and linear collider effort, that means the ILC, are coupled together in the framework of the linear collider study at CERN. Because the third topic in the European strategy, high priority, is the International Linear Collider, where they have finalized the technical design report that has been completed. Construction could in principle start, but we have to find somebody who would like to build it. Now Japan has expressed interest, and Europe at least looks forward to a proposal from Japan to discuss a possible participation. So that's number 3. And at CERN, there is the effort on the ILC is in the framework of the linear collider effort together with the CLIC effort. Now the 4th pillar of the European strategy is that CERN should develop a neutrino program to pave the way for a substantial European role in future long baseline experiments. We should explore the possibility of major participation in the US and in Japan. So our idea is, with E plus E minus, from Europe, we look to the east, to Japan. For the neutrinos, we look to the west, to the US. And we have now created a so-called CERN neutrino platform, which enables large-scale detector development and tests for neutrino detectors. So the Icarus detector has now been moved from the Gran Sasso to CERN and will now soon move refurbished to Fermilab to build part of the short baseline project. And then we have other liquid argon detector R&D ongoing. So there's a test beam now dedicated to neutrino detector R&D, in particular liquid argon. And we have started now very well the collaboration with the US, in particular, of course, Fermilab, concerning long baseline neutrino facility, or the latest name is DUNE. There's a common effort on detector and accelerator topics. I'm happy to report that a global collaboration has been set up now. That's a major breakthrough for Fermilab for the future. It needs now a long-term sustained effort and support, but as far as I understand, DOE is very much behind that subject. So that looks very encouraging. So we have a clear collaboration now with Fermilab, or with the US on the LHC, and now in the other direction with the neutrinos. So particle physics in the next decades has a fantastic future, because with the European strategy approved by our council in May 2013, with the P5 recommendations, which were approved by HIPAP in the US last year, with the Japanese roadmap, we have, at least to my knowledge, for the first time, a global vision for our field, and which goes far beyond regional boundaries. So this is really for the first time that we have this common vision. So CERN, of course, will play a major role in this global endeavor in all directions. That's also new at CERN, that we go beyond our borders, so that we go out of our dedicated site in the Geneva region. So CERN is there to innovate, to discover, to publish, and to share. And I think one of the main issues also is that CERN is there to bring the world together. Thank you.
Okay, thank you for this wonderful talk. So now we're open for questions. Right there.
What do you see as China's role in CERN?
China's role in CERN or in general?
Just you mentioned Japan, the United States.
Well, we are collaborating with China on the experiments. We have good relations with China. Now the question is, how is China moving forward, for example, with a circular collider? Is it to be seen as competition to the IRC in Japan or whatever? We are open for collaboration, intensifying the collaboration with China. It depends on their way, how they want to move forward.
You mentioned that the new data from the LHC could give evidence for supersymmetry or for more information about dark matter or dark energy. How likely do you think something like that is?
Well, he's asking me how likely I think the discovery of supersymmetry or some more information on dark matter in general or dark energy would be in the next years at LHC. That's the main. That's his question. Now my answer is I don't know.
Well, you put it on your slide, so you think that it's at least not zero.
Well, I hope. I had the exclamation mark and had the question mark. Okay. The difference to the Higgs is that the energy range of the LHC was chosen so that the electroweak symmetry breaking mechanism would fall inside this energy window. So it was sure that we would find the reason or the mechanism how elementary particles get their mass. That was given from theory and experimental knowledge. So it was sure that we would discover something, either the Higgs or something else. Yeah, now it's a Higgs. With dark matter, dark energy, it's much more difficult because the predictions are so wide. Our theory colleagues are very clever. They have a plethora of models because supersymmetry is not just a single model, it's many, many different models. So that you don't know where it is. It could be at very high scale, it could be at a relatively low scale, and this is exactly where I don't know. But I'm always an optimist. You cannot be a director general without optimism. Yeah? No. There is a high chance, but it's not actually that is it's for sure. But it's basic physics. And basic physics has the risk of not finding something, despite all your best efforts. But I'm pretty sure that we find something. I don't put any pressure on my successors, but I'm pretty sure we find something.
Okay, question back there.
So, can you comment on how the science goals for the linear accelerator discipline are different from those at previous or at circular accelerators?
Well, first of all, the linear collider uses electrons and positrons. The circular collider at the moment uses protons and protons. Ignore for the moment the heavy ions. So in the older times, I would say 10 years ago, everybody said the proton-proton collider is a discovery machine and the E plus and minus collider is a precision machine which studies that physics. I think that's no longer true. Both are precision machines and they can discover things in the different production modes. Okay? For example, the carrier of the strong force, the gluon, was discovered at an E plus and minus machine. You would have expected to discover it at a proton-proton machine. So both have discovery potential and both have potential for precision measurements. The key issue here is that you look at the same questions but with a different view angle. You come with a different production mechanism, you look with different types of detectors, and you look with different backgrounds in your processes. It's very similar to astrophysics or astroparticle physics, where only the results from many telescopes together give you the final picture. The same here. You look from different view angles, and suddenly you see much more. So it complements the proton-proton through the linear collider E plus and minus. The question is which energy? If you want to study many of the Higgs couplings, you can choose an energy of 250 GeV. But then you miss the TT bar threshold, for which you need at least 350 GeV. if you want to measure the triple Higgs coupling, which is something very important, that's the decay of the Higgs into two Higgses, you need at least at the E plus E minus 800 GeV, maybe much better. It's even better to have 1 TeV. This you can only reach with a linear collider. Now, so already the Higgs only gives you enough justification to study it also within an E plus E minus machine. Now here you have to see which energy you want to use. The result of the next run, if we find something about supersymmetry, if it's low mass or higher mass, that will then finally also decide which type of accelerator you build.
More questions? Yeah. Oh.
CERN has had a very successful program of heavy ions. As the energy and the luminosity increase, what do you see as the future for heavy ions there?
Well, at the moment they have a program until at least for another at least 10 years. And then we have this long shutdown where we increase where we have the high Lumi upgrade. And even there, you could imagine to run from time to time also for heavy ions with a higher luminosity. They have plans to collect 10 inverse nanobarn with the in the heavy ion collision mode, which would go until 2030 or so. It complicates a little bit the design of the interaction region, but it's possible. We are in discussion of that. And if they have a clear, structured, interesting program, I think one can do it. So I see a long future also for the heavy ions at LHC.
The detector upgrades might need to be different.
At the moment, they are upgrading their detector or improving their detector every shutdown. They also have a very ambitious program for the next shutdown. And I think then they should do one step after the other. First, finish this the present upgrade before they talk about the next upgrade. Otherwise, you lose the focus, and then they have a problem. But I think there will be a long lifetime also for the heavy ions. And actually also in two experiments, LHC, CMS and Atlas, there are two heavy ion groups very active. Yeah. Now here we have to decide, do you go on with these activities or not? That again complicates the interaction region. Okay, if you are willing to pay for that, that's no problem. No, we have to discuss this, but it will go on.
Right, any other questions? Maybe I can ask a quick question. So suppose the projects in China and Japan don't go ahead. What are the plans that CERN has to go to higher energies? Is the high energy LHC still in discussion?
Well, I didn't have it on my transparency that the FCC study includes a high energy LHC. High energy LHC means you throw out the present magnets in the LHC, replace them by new magnets. Now, given all the efforts in magnet technology, you might reach a maximum of a factor 2 higher energy as a high energy LHC. Question, is that enough or not? So this is why we concentrate at the moment concerning the energy frontier on this, let's call it 80 to 100 kilometer infrastructure, which would give a factor 7 or 8 with respect to the LHC, depending on the magnet development which you can do. The diameter, the circumference would be a factor 3 more than the LHC roughly, which is not so much, plus the new technology in the magnets. However, we have to see how much it would be, how much it would cost. But that is at the moment one way we are looking at. But we are looking at that independent of the two other countries.
Okay, any other? Oh, yeah.
Why do you think it was particle physics as opposed to a different area of physics or science in general that was able to bring together the kind of financing and need for international collaboration to create a huge project like this?
You mean why it was us, particle physics? It's in our genes. No. I don't know. I mean, particle physics from the very beginning on the experimental side needed larger and larger cooperation, larger and larger collaboration. So we have to some extent learned how to deal with this. Experiments 20 years ago, 30 years ago, consisted out of, the big ones out of 300, maximum 500 people. We thought that's the maximum. But we learned how to cope with that. Today we have the 3,000. It's somehow, we have learned, obviously very quickly and in a steady manner, that you need to collaborate despite the fact that you compete at the same time. I don't know why it's us. I see big problems in other areas of science where they have problems to work together in such a way. But I think it's unavoidable for most of the scientific fields to collaborate more. Take photon science. If you go to the free electron lasers, it's not a group of 1 or 2 or 3 people. It's now also rather big experiments. And I don't know, for them it seems to be a learning effect. I don't know. It must be in our genes. I come back to that. I have no other explanation.
Okay, then let's thank Professor Heuer again.